Okay, so the first thing that I did was I matched the real part of my load. I started out with a load that had neither the real nor the imaginary part matched. I rotated a distance d towards the generator until I landed on the matching circle of the Smith chart. There were two places. There was ZA1, or I could have used ZA2. In this case, I decided to have d be the shortest possible length, so I stopped at ZA2. And then I found the distance by reading on the outside axis in the wavelengths toward the generator. I subtract 0.32 off from 0.21, and that tells me the distance that I need to go. Now let's see what my imaginary part is. Right here, I'm at ZA, and I can read the real part. So for ZA, the real part is 1, just as I wanted, and let's read the imaginary part. Looks like that is about 1.7, and it's negative J 1.7. If I want to get this in ohms, I would need to denormalize it by multiplying by Z0, but I don't actually need to do that. In the next step, what I want to do is add on a stub which has the opposite value of the imaginary part that I have, because I want to end up with 1 plus J0. So the stub, here's my real part here's my imaginary part right now. The stub is going to be normalized 1.7. Let's find it up here. Here's 1.6, there's 1.7. So here's Y, a Z, of my stub. Now in our next picture, we're doing a series stub match like this. We have rotated our distance d, so we know what d is, and we know what the input impedance of the stub needs to be, and that is J 1.7 normalized. So let's draw it again right here. 1.6, 1.7. Here is Z at the input impedance of the stub. Now let's consider an open-circuited match. Here's ZOC right there. You can look at this stub as a separate transmission line, where this is the input impedance and this is the load. So I'm just going to write load right there and input right here. If I want to go, let me draw my stub a little bit bigger so that we can kind of talk about it. If I want to go from my input to my load, that is towards the load. If I want to go from the load to the input, that is towards the generator. So if I am at my load and I want to go to my input, I'm going to go towards the load. I'm sorry, if I'm at my load and I want to go towards the input, I'm going to go towards the generator. So here I am at the load. I want to go towards the generator, like so, until I reach my input. And that's going to be the distance L, the length of the stub. Well, let's calculate that. L is going to be this value, and I'm going towards the generator. So I'm going to read the towards the generator axis. It's 0.25 minus, well, when it came out here, this was 0.5, and right here would be 0.57, 0.62, and right there is going to be about 0.665. So, oops, I'm doing this backwards. It should be 0.665 minus 0.25 wavelengths, and that's the length. Now I tell you, there is actually an easier way to calculate this distance. The other thing that I could do is I could see the entire length of the Smith chart and just realize that I want to subtract off that distance. So I could have taken 0.5 minus this value, 0.25, minus this value, 0.165, and gotten the same thing, just maybe a little bit easier.